chaos theory and the butterfly effect. Okay, so this presentation, I'm going to talk about chaos theory. It's a bit of a complex topic. Originally, it was designed to be 40 to 50 minutes. I gave it in 2019 in When Worlds Collide. Then I'm going to give some example on how to use chaos in your writing, either as part of the plot and also in your writing process. But again, since it's a lot of topic to talk about, the focus will be what is chaos theory. And chaos theory lesson to improve your writing. What I'm going to talk is based on the book, Chaos, Making of a New Science. You can see it here on the slides. And of course, if I'll put it on YouTube, you can get a view of this recording, and I can give the name of the book if anyone wants to expand his knowledge about chaos. The science revolution of the 20th century has three major revolutions that change the perspective of scientists on how the universe works. First one was relativity, about time, that about speed of light is the fastest speed, and gravity. Then it talked about another theory that changed our view of the world is quantum mechanics, that everything is finite, small quants, the subatomic particle. And the third one is chaos, which we are going to talk about today. And we're going to start with lesson 1. Tiny changes can have a huge impact. Now, when I was a kid back in Israel, we had a translation of Hebrew of this song. And this is a song from the Middle Ages. It's talking about how tiny events that nobody counted have a huge impact in the future. So according to the proverb, a messenger was sent before a battle to call for reinforcement, and then a nail fell off the horseshoe, and he couldn't deliver the message. Because he couldn't deliver the message, the reinforcement couldn't come to battle, and the battle was lost. Because the battle was lost, the war was lost, and the king lost his head and lost the kingdom. So a huge historical event happened because of a tiny little event. So this is what chaos is all about. Everybody watch the weather. We know the weather is something that is very, very difficult to predict. Like if you look at the weather, sometimes they're right, sometimes they're wrong. And if you look more than 2 weeks into the future, then it's completely wrong. Like it's not entirely, we still have climates. We know that the winter is typically colder than summer. But if you look at the weather forecast, it could be kind of accurate in the next 2 or 3 days, maybe a week. Longer than that, yeah, we have no clue. It all started in the 1960s. Edward Lorenz and the butterfly effect. Back then, a new technology was coming forward. It was called the computer. So they had some of the biggest computer that IBM delivered. And before that, during World War II, when scientists or weather meteorologists tried to predict the weather, it was kind of an art. They saw cloud patterns, they tried to suggest, based on knowledge from history, from elderly, what the weather is going to be like. But in the 1960s, Lorenz was trying to put a model within, back then he used 12 functions, today they use more than 50. And then he tried to have weather station around the world or around the region. He collected the data, and based on the data that he collected, he ran it through a computer, and then he tried based on that to predict the future. What science thought about how prediction is working, and that you have the initial condition, like what the data that we have from all the weather stations, and we have the rule of the system, that's the 12 equation that and then he fed the data into the system, into the computer, and ran the 12 equation. And based on the data and the rules of the system, you can predict a future state. So he ran the data, he got some prediction, then he broke for lunch, came back after lunch, and he tried to repeat the experiment. So he fed the same data, and then he saw that the result was completely different. You can see initially here in this part of the lines, the data was pretty similar. I mean, the end result was pretty similar to what you got on the first one. But then as time passed, like 2 weeks later today, and we know that we cannot predict weather more accurately more than 2 weeks into the future, the data began to deviate. And that was a question he didn't understand why. So what it turns out is that he rounded the number. Initially, he put a number with 6 digits, and then when he ran the equation again, he put only 3 digits. And this, even though the difference between 3 digits and 6 digits, it's very, very tiny, less than 0.1 of a percentage. If you look at the functions long enough, you saw that the results was completely different. That's again like the fable about the nail. One nail can have a huge impact on the future. Here, you take almost the same data with tiny changes in sub-fractional 1 divided by 10,000 or so, and you get a completely different results. So Lorenz was that was the beginning of the chaos theory. So it became more famous in the 1970s, but the 1960s, that was the beginning. So we had computers, and we saw that tiny changes to the initial condition can have huge impact as time passed. And now we go to one example from fiction. Everybody probably remember the movie Jurassic Park, when Dr. Malcolm explaining chaos theory while flirting with Dr. Ellie Satter. So I'll just read it from here. Dr. Malcolm, Dr. Satter, Dr. Grant, you heard of chaos theory? No. Non-linear equation, strange attractions. Dr. Satter, I refuse to believe you that you aren't familiar with the concept of attraction. So I'm going to talk to you about attraction, but it's nothing to do with romance. Back to math. Lorenz strange attractor. So first of all, Malcolm was lying. It was not attraction, it was attractor. So they have two concepts. One is unpredictability. The initial state of the rule aren't enough to predict the future. That's exactly what we saw with the weather. So we know the rule, we know the prediction, but the prediction will not be accurate. It also happened in Jurassic Park. Nobody expected the dinosaur to go away, to start eating people. But the doctor who was familiar with chaos theory knew that the future cannot be predicted. The second parameter is a periodicity. It means that the system never repeats itself in quite the same way. One example of chaos theory, you need 3 nonlinear equations. You see this wheel here on the right. The idea here that you have buckets. The buckets could be filled with water, and there is a hole in each bucket, so the water comes out of the bucket. Also, the whole bucket can spin, and there is some kind of a water pump that throw water into the buckets. So we have 3 elements here. They are not linear. The water that comes out of the bucket, it could come fast or it could come slow. If it's almost empty, it will come out slow. If it's almost full, it will come fast. If it's spinning, of course, it will change the speed that the water comes out. So it's non-linear. And when you have 3 equations that are non-linear and put them together, it's very, very difficult to predict how the system will behave. We don't know how fast the wheel will spin and to what direction and how much water will be in the bucket. We don't know what going to be the future position, the future prediction, how the system is going to look like, even though it seems like pretty solution. And it's similar issue with the 3-body problem. Kepler and Newton, if we have 2 bodies, like a sun and a planet, or a planet and a moon, or a binary star, we know very well how to predict how they're going to spin around each other. But if we have 3 bodies, then it's completely different question, a lot more complex. There was also a book that won the Hugo in 2015, I believe, 3-body problem. So here we see how a computer draws a diagram based on 3 nonlinear equations. And we can see it look like a butterfly. Again, attractor. The system never repeats itself. We cannot predict exactly where it's going to look like. It could be here, or it could be here, it could be here. But again, it's still within a boundary. Like we are not probably not going to have a snowstorm in summer, but it's still, we don't know if it's going to be 30 degrees or 15 degrees or if it's going to be sunny or cloudy. We cannot predict, but the system cannot have a boundary. So we do know how to predict climate, but we don't know exactly what the weather is going to be like. A little bit of literary discussion. The Foundation, 3 weeks ago, it came out in Apple TV. I'm sure a lot of people here read the book. In the book, Asimov was talking about psychohistory. That's a science that can predict the future. And according to what Asimov, by the way, wrote the book in the first book in the 1940s. So he wasn't aware of chaos theory that became known in the 1970s. So according to Asimov psychohistory, humans are like a gas molecule. They predicted that the galactic empire is going to collapse, and the event or what one person will do doesn't really affect how it's going to unfold, but how the masses progress. This is how the history is going to unfold, and it was pretty correct until the half of the second book, and then he noticed that it's not exactly accurate, so he added the mule and make it a little bit more interesting. So Asimov was wrong, but we don't blame him because he wrote the book about 30 years before chaos theory became popular, and 20 years before even it was conceived. A little bit more of discussion, literary discussion. One short story that I like to explain chaos theory, or at least the first principle of chaos theory, that one small change can cause a huge impact. One butterfly that died in Brazil or flip his wing in Brazil can cause a tornado in Kansas. The sound of thunder. I hope it's a story what was written in 1953. I hope I can tell stories. In the story, a group of people travel back in time to try to hunt the dinosaurs, but they picked always dinosaurs that were about to die anyway. So they come 5 minutes before they died, and then they hunt them. And the idea was that history wouldn't change as long as they stay in the same track that was designed for them and do exactly what they are told. But then something happened, and one of the people ran out of the road, and he stepped on a butterfly and killed the butterfly. And then when he come back to the future, to when he originally come from, the history was completely different. The language was different. All the politicians were different. So he made a huge change just by killing one small butterfly. Chaos theory, that was a romantic comedy, butterfly effect, time travel romance, Back to the Future. This is probably a lot of more people saw the movie. Back to the Future, and Back to the Future, when Marty went back in time, he knew that just by falling from a tree, he changed the event that his parents met, and then his mother would marry his father, and he would be disappearing along with his brothers. So he was trying to mend everything together to prevent this tiny event in the past that could have a cascading bigger and bigger effect in the future. So we can maybe later discuss a historical event, but like if killing Hitler would have prevented World War II, there is a debate among historians, like if Columbus didn't leave, would America still be discovered? So they say, yeah, maybe not in 1492, but maybe 10 or 20 years later, America would be discovered anyway. But killing Hitler, or maybe one tiny virus killing Napoleon, and then all of history would be different. So there is still debate about historian how accurate chaos theory is. I say that it is. Small change can have huge impact on the future. So how can this be applied for your writing? You must have chaos within you to give birth to Dancing Star, Friedrich Nietzsche. So earlier we spoke about how to use chaos theory as part of the plot, like in Back to the Future or the Sound of Thunder or Jurassic Park. The chaos was part of the story itself. But you can also apply what we learn into the writing process itself. So let's say you write an outline, you don't want to have a very rigid outline and stick to it. Like if you see that a plot is evolving into a more interesting area, go with it. Let's go with the flow. It's a you want to add a little bit chaos into your writing to have a more interesting impact on your story, the story that you write. Use unpredictability and periodically in your plot, so the reader cannot predict exactly what you wanted to do. You want the reader to get to a point that is especially critical in murder mystery, but also in other genres, that he cannot say, yeah, I know from the beginning who is the killer. That's not going to have a very good story. But you want the reader to be surprised, but still have enough clues that you say, yeah, oh yeah, why didn't I think of it? I should have thought about it. Applying a little bit chaos into the writing process. The other two lessons, this is the last two lessons that we're going to talk about here today. I'm going to combine them. One is that complex systems are based on simple behavior. You can have very simple rule. You can also apply this to writing. The characters want one thing, or he lean into one thing. And then just by having one simple rule, you can have a very complex system, very complex plot line, or very complex world based on just one rule. And the lesson 3, law of complexity hold universally. That means that if you, this specific system, let's say in history, behave in a certain way because of chaos, it's also working the same way in finance, it's also working the same way in biology and in many other fields. And the reason I did this presentation is that perhaps chaos theory can also work in writing. And I don't remember, 1916, 1917, the US Army was trying to find, to do noise cancellation. So if you have a network with noise in it, you're trying to do some kind of technology to do noise cancellation. So some scientists started to analyze the noise in a system. It could be in a cable line, it could be in a radio line. And what they discovered, that there were interval of noise and then interval of quiet. Noise, quiet, and they were more, not exactly, but more or less similar. And then they analyzed the noise interval, broke it down to noise interval. So here you have a period of noise, period of quiet, period of noise. And then they just look at the noise. And they saw that even in the small interval of the noise, it was broken down to times that the system was noisy. There were a lot of interference that they tried to cancel or correct, and period of quiet. And the pattern here look very similar to the pattern here. And then they look at this pattern. And they see that this smaller chunk of noise within the bigger chunk of noise is also have a time where it was more noisy, time that it was quiet. And the pattern was very, very similar. The pattern here is similar to here and similar to here, and vice versa, as long as you go down. So the same pattern, very simple behavior, is going into different levels of time interval. And this works not only in noise on a cable, but also in other area. Next, I'm going to show you a video. Now everybody can relax. It's almost like doing meditation. But what I'm going to show you that are 3 nonlinear equations. They do a pattern and they have a very, very simple equation that generate very, very complex pattern. And the second thing you can see that as you zoom in, the pattern is very similar to how we saw the noise. It's very similar. When you zoom in, the pattern is very similar to the big pattern, the small pattern. So the next one is how do we measure factual geometry? And Mandelbrot Set is the video you just saw. If you look at the map of Britain and you take, let's say, you try to measure how long it takes to go around it, and you take 100 kilometer sticks, 62 miles, then you get that the external of Britain is 28,000 kilometers. But if you have smaller sticks, 50 kilometers, suddenly Britain become bigger. It's 3,400 kilometers. And then you can go smaller and smaller up to get even to a size of a, if you measure around like every sand or every stone, then you get a very, very, very long island to walk around. So the number of how it takes to go around Britain depends very much on what kind of measurement you're doing. So very similar to snowflakes. Snowflakes also, you can measure it like this, or go into deeper, or go deeper. Next item is Feigenbaum constant. That's another constant, interesting. We have equation here. That means that in a certain year, this is what happened. That's the equation, and then we try to see how it looks when you do a graph. It could be used, logistic map could be used for many aspects, but for example, to make it simpler, let's talk about biology. Let's say we have rabbits, and in year n+1, next year, we're going to have the same number that we have before, times lambda. And lambda, to simplify it, it's the number of baby rabbits each rabbit has. So let's say if rabbit have 3 baby rabbits, or 2 rabbit couple have 6 rabbits, the number here, the lambda will be 3. But then you need to put another area. Let's say all the rabbits are in one island. So if there are too many rabbits, then they don't have enough food and they die. So this is a limiting, the second part is a limiting factor. So of course, if we know that if in each generation we have each rabbit bring less than one rabbit, then the population will shrink, because every generation will be smaller than the previous one until all the rabbits become extinct. If you have more than a baby rabbit for every rabbit, then the population will grow until it reaches a plateau when there is not enough food for all the rabbit, and then it's going to be stabilized. So this is what happened, and you have between 1 rabbit and 3 rabbits. But once you get to more than 3 baby rabbits for every rabbit, then it starts to behave in a different way. Instead of stabilizing on a plateau, it starts to get into these 2 points. So this is when R, or lambda, is 3.25. That's what happens if you have between 3 and 3.5 kids. But the real interesting picture is what happened when you have 4 kids or even more. So again, if you have less than 1 kid, the population eventually will extinct. If you have between 1 kid and 3 kids for every rabbit, then the population will stabilize at a certain size until here. It cannot get to here to 100% because they don't have enough food. And if you go beyond 3 rabbits, then it going between 2 points. 1 generation here, 1 generation here, generation here, generation here. And if you go more than 3, more than 3.5, it's starting to behave in a very, very weird way. This is actually being used in generating random numbers. But you can see from the pattern that this area here, between 3 and 3.5, it's very similar to this pattern here. And if you, I cannot zoom in here on the picture, but this pattern here, it is similar to this one, it's similar, but it's become smaller and smaller and smaller, and there's the same pattern here, it's getting smaller, 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 until it gets totally crazy. That's a bifunctional diagram. Back to Feigenbaum constant. If you look at the number between this point and when we go to 3 and 3.5, and then divided between here and here, when it starts to split again, and then the pattern repeat again. So each time the pattern repeat again in the smaller scale, the ratio is 4.669. This is Feigenbaum constant. If you remember the movie that we saw earlier, the big pattern, then you have pattern number 2, pattern number 3, pattern number 4. It's getting smaller, smaller, and smaller, but the ratio between the big picture and the smaller picture, when the pattern that repeats, it's again the same golden number, 4.669. And this is very predictable in different formulas and different equations. and different scenarios. I have about 5 minutes left. So the same chaos theory works in the same way in different fields. In ecology, animal population, similar to what we saw now. Biology, if you look at veins, we have the big vein or electricity or brain synopsis or tree branches. Tree branches is a good example. You see the big branches and then you split to the small branches and the tiny branches. So the small branches looks very, very similar to the big branches, only a lot smaller. And they also carry the same ratio, not always, but on average, the ratio of 4:669. It's the same going in finance, in economics. I'm sure Sandy will tell you it's very difficult to predict the future, but sometimes if you look at a yearly pattern and or monthly pattern and weekly pattern and minute by minute, it looks kind of the same, the way stocks or indexes are working. Meteorology, weather prediction, also cloud pattern. In chemistry, condensation, snowflakes. If you zoom in very, very small, the crystal look very similar to the bigger snowflakes. In physics, the galactic orbit looks kind of similar to electrons. So same patterns, same chaos theory can be in different fields. How can we use this in writing? Again, writing have different areas: word choice, sentence, paragraph, scene, chapters, book series. And we can do the same in plot line. Again, as I told earlier, when the characters want something, so it could go in small scales and large scales. Lesson learned. Laws of complexity hold universally. Conclusion. Before chaos, we believe three things: that simple systems behave in a simple way, like small change will have a small impact, similar to how Asimov predicted the psychohistory will behave. Complex behavior implies that the rules are very complex. Like if you have brain, then DNA that created the brain must be a lot more complex than the brain, but this is not true. And different systems behave differently, like economics behave different than biology and different than writing. But what we know after chaos, simple system can cause complex, unpredictable behavior. Small changes can have huge cascading impact. Complex system could be driven by simple behavior, like brain synopsis, and laws of complexity hold universally. That was the presentation. I'm going to stop sharing. So Michael, you can have it back. If you want, I can answer some question, or we can do it later in the pub, because I believe we have some additional agenda items. The pub, I mean, after the meeting.
Well, I think we can go 5 or 10 minutes with questions and answers if you like, if anybody has any.
Yeah, I have one. I'm wondering if maybe this is more a philosophical question then, but does that mean there really are random events, or just events that we can't predict?
Yeah, that's the first law. Similar random event we cannot predict, and small event we cannot predict the big event because we don't have all the initial condition. We don't know where all the viruses in the world at this certain point of time and how they could affect. But what we do know is that small change that we didn't measure because it was so tiny can have a huge impact. This is what the first thing we know about chaos theory.
Okay, but so I'm asking it from it's theoretical, but with infinite knowledge, can you predict the future then?
I would assume yes, because
Okay.
one of the other things is that quantum mechanics, that there is a finite number of particles in the universe, but how exactly you're going to build a computer that have all the particles in the universe and all the subatomic particles and all the photons and everything.
Yeah.
So we may not know it ever.
I would suggest if you're writing a novel and you want more than a simple plot, you need to lay out your plot with all kinds of little breadcrumbs and things to give you red herrings, give readers ways of thinking, and then pull the rug out from all that. But they can never be random, I don't think. You never want to throw random stuff in your writing. They all have to be, what's the word? They all have to be earned.
They have to be earned, but sometimes if you have a new thought that takes you into a new direction, you don't reject it just because it's not in the outline.
No, that's true. But if you want to make your story a little more chaotic, those events that you're inserting, those random events, they can't be just random.
Renee wants to say something?
I'd say that yes, you can put random things in, but you have to make them make sense eventually. They have to fit.
That's what I said. They have to be earned.
No, not necessarily earned. They have to fit.
It's like a Kia.
It's a slightly different way of looking at things.
Don't do the
When you're talking about earned, I'm thinking about what the main character does. I'm talking about random things that show up in your story, which may or may not be something that the main character does, but it does fit. I'm thinking in particular about certain mysteries where you get a random assortment of clues, and it may make no sense when you first start it, but eventually it fits, and that's not earned, except in as much as the main character learns about what's going on.
Yeah, and then you remember the example, like the butterfly, it's still within the pattern. It's not predictable within the pattern, but it's not going outside the pattern. Like the wheel with the buckets cannot go faster than the speed of light. It will go at certain speed, but we don't know exactly what it is. But it's still within the boundaries. Any more questions?
Sometimes random events work quite good in comedy, though. I mean, a lot of Monty Python's humor is based on completely random acts that just throw you off, come out of nowhere, and that what makes you laugh, right? Well, I guess that's not a serious application of randomness.
So they have a wider boundaries. I remember the life of Brian, that he fell from the mountain, Brian, and then from a roof, from a tower, and then a spaceship came and picked him up. It was totally unpredictable.
Ron, I'm
Has no
also,
effect on this.
Let's wrap up with Carl there, and then
Okay.
we'll move on.
Carl and Barb both have their hands up. Carl?
Yeah, just a second. Yeah, Randall makes a very good point, okay, about how do you incorporate this in writing, and Ron's made an effort to do that. Personally, I find this an absolutely fascinating science, and it's one that I understand quite well, actually. And I think it would make an incredible plot line for a character that is able to see into chaos, because chaos is really nothing more than apparent random states of disorder and irregularities that are governed by a deterministic laws. And if you determine those deterministic laws of these random events, what you have is a system based on a highly sensitive to initial events. And so if you build a storyline around that, I think it's terrific. So thank you very much for that, Ron.
Yeah, I think Jurassic Park is a very good example.
Yeah, right.
And Barb, you have a hand up.
Okay, so I just finished my MFA, and I've been doing 2 years of reading / for OnSpec. So I've read a lot of stories in a very short period of time, and I have to point out how very important it is that when you're coming to a decision in your story, there's 3 doors. The first door is if any writer came up with the idea, that first door would be the first obvious outcome of the situation. That any, like if you pull 100 authors, 90 will choose door number 1. So don't choose door number 1. But then don't do the opposite of door number 1. So if they burst into the door and everyone would say, oh, he meets a dragon, don't then kill the dragon and say, oh, he burst into the door and there's a dead dragon. So avoid the most obvious solution and the opposite of that most obvious solution, and then find a solution that oscillates somewhere between those two, so that at no point could the reader think, okay, that's obviously what happens. But to mention to Renee's point, yes, you can put anything anywhere, but if you look at the book like a triangle, what happens in the first half has to be reflected in the second half. So something can happen very randomly in the second half of the story, but if you foreshadow it twice in the first half of the story, it will always feel like it belonged there to begin with. But you don't do foreshadowing from the first draft. Right? First draft, the best place to put the foreshadowing is in the rewrite. So don't worry about doing something completely random in the second half of the story. You can always go back and foreshadow it.
You got that.
That's actually a good idea. Maybe
Yeah, very good.
I'll steal it. Okay, so thank you very much, and I'm going to stop the recording and back to you, Mike.
Cool.